After going through the basics of finding the vector equation of a line, whether you're given 1 point and a parallel point, or 2 points, or a point and the normal. So we're going to have a look at several types of questions that you will be asked. So we've done the basics in the previous video, but now we're going to look at different skills. So first, take a pause, read through all the skills that are required, and I'm going to explain through them. Each slide is then followed by the actual written solution, so you can skip through my explanation if you feel like the question is fairly straightforward to do. Again, I would encourage you to attempt the question on your own based on what you think you should do. For example, well, based on the definitions, do you apply it here? Do you substitute to there? Because that will really reinforce how much do you understand about the structure of vector equation of a line. So do pause the videos, try the questions before listening to my explanation. So if you're given the in 2D, you're given the line and it needs the vector equation of the line. So in this case, keep in mind, what do you need from the vector equation of a line? Remember that we need a point and a parallel line, or 2 points. Well, let's actually try finding 2 points. Can you find 2 points if you're given a line? Well, this is fairly easy, quite basics, something you've done before. So to find 2 points, substitute any x value. I'm going to substitute a 0. If I substitute a 0, it's going to give me a 2. That's 1 point. I can call it A. And then another point, I can substitute a 1. It's going to give me a 5. That's another point. So I have 2 points here, and we know what to do with 2 points. If I want to find the vector equation of a line, I first need the direction vector, and that's going to be 1, 5 minus 0, 2. So that's going to give me 1, 3. So that's my direction. And therefore, if I need the vector equation of the line, it's going to be the point, any point. Let's pick 1 and 5. And then lambda 1 and 3. And lambda being a real number. That's it, quite fairly simple. You'll notice in some solutions they do it slightly differently. For example, they decided to pick 0, 2 as the point, but I picked 1 and 5, which is fine. So do compare what I'm doing with some of the solutions just to see how you could possibly do it differently. This time we're reversing it. Obviously it's the same points, but we're going to reverse it. This time I have the line in vector form, and I need it in Cartesian form. So Cartesian form would be your the normal y equals to mx plus c form. So in order to do that, this is the vector form. So you can change it to parametric, then Cartesian, and then rearrange it to gradient intercept form. I will immediately go to the Cartesian form of a vector equation, which is just taking these as the denominator, and then I have x minus 0, and then y minus 2, and then I'll just make y the subject here. So I have 3x equals to y minus 2, and y is equal to 3x plus 2. Okay, which if we check, obviously this is the line from the previous question, by the way. So if we check, it actually gives us the actual line that we started with. So it is actually correct. All right, another skill is to, if I'm given the equation of the line, I need it in a gradient intercept form, and it passes through this, but I'm given two different descriptions. One, that it has to have this direction vector, and another is that it has this normal vector. The first one is fairly simple, repetitive. We've done this, so -3, 4, lambda, 2, and 1. So make sure that you write this if you want to in component form. You can write it in algebraic form as well if you need to, but then they need it in gradient intercept form, so I can immediately switch it to Cartesian form, and say this is x plus 3 over 2, and this is y minus 4 over 1. I'll skip the algebra here. I'll make y the subject, and that's going to be negative x over 2, 5 over 2. So that's me writing it in gradient intercept form. Now for the normal, remember the equation that we had in the previous lesson. It was u taking n scalar product p, and then n scalar product with your point A. So I know what the normal vector is. It's 3, 5. The point is just x and y. And then again, 3, 5 with scalar product, negative 3, 4. This is the point that is given in the question. So how do we actually simplify this? Sometimes we leave it as this if you're given, and if they're asking it in vector, as in the normal form with the vector. But we need to get it into gradient intercept form, so we need to actually solve this. So what you're going to do is actually take the scalar product here, which is, remember, you multiply component y, so 3x and then plus 5y. And then in here, 3 times negative 3 plus 5 times 4, simplify this, and it's going to give you 11. And then I need it in gradient intercept form, make y the subject, quite easy to do, minus 3x over 5, and that's it. You have your final answer. I only put the solution to part B because part A is straightforward. Next skill is about finding the intersection of lines. So I know 2 lines and I need to find the intersection. And they're given in different forms. The first one is in vector form, and the second one is in Cartesian form. So how do we find the intersection of lines? Think back to how you would actually do it when you have it in 2D, in y equals to mx plus c form. How would you actually find the intersection between the lines? So based on how you understand that, you should be able to get a hint on how to solve this question. So people solve it differently. I'm going to solve it differently than the solutions on the next slide. What I'm going to do is I'm going to write it in gradient intercept form and then do the normal intersection between them. So I know that R is 2, negative 5, negative 1, and 3. And I know that if I write this in Cartesian form, it's going to give me 2x minus 2 over minus 1, and y plus 5 over 3. And rearranging it, I'll end up with a negative 3x plus 6, and then and 1. So we have that. So once I have, this is the equation of the first line, then I'm gonna do it again for the second one. So this is my first equation, and then do it for the second one. I will you can skip through these parts. So once I rearrange this equation, so I end up with y equals to a minus x over 3 and a 1 over 3. So just I'm skipping a few steps here. So once I have that, then I will, this is my second equation. So I have 2 equations. I can make them equal to each other to find my y value, for example. So I have negative 3x plus 1 equals to negative x over 3 plus 1 over 3. I'll solve it, simplify it, make x the subject, whatever. So I'm skipping some of the algebra here. You end up with x equals to 1 over 4. Once x is equal to 1 over 4, replace it with any of these two, and you get y equals to 1 over 4. So it's just basically simultaneous equations. But the point was to start from here and get to your gradient intercept form. So once you have that solution, that will be the intersection, the point of intersection, which is 1 over 4 and 1 over 4. You can have a look at the solution. It does it slightly differently, but you end up with the same answer. Next we have whether or not these lines are concurrent. So concurrent means that they intersect at one point. So you have all three lines, and do they all meet at one single point here? Well, let's start with actually just taking 2 lines at a time. We won't be dealing with 3 lines at a time. 2 lines at a time, find their point of intersection, and then decide if it fits with the third line. So we'll take the first 2 lines, and I'm going to skip these steps because it's similar to the previous question. But the first 2 lines, so L1 and L2, if I do the point of intersection, they will have 1 over 3 and y equals to -2 as a point of intersection. So we have that. Now we want to check, does it also fit here? Which is a common question. Does this point fit in my line? Well, let's see. Can you find the point is there a lambda that I can substitute here that will end up simplifying this to give me a 1 over 3 minus 2? That will confirm that 1 over 3 and minus 2 belongs on the line. So we will set up the equation. So let's say 1 over 3 and minus 2 is equal to -5, 6 plus lambda 2 and -3. And we're establishing, does this work? You end up with 2 equations. So, or you can simplify this. You can move this to the other side. These are not matrices, by the way, so you can move them as such. Think of them in component form. It's easier to see how the subtraction works. And then 2 minus 3. So you end up with 16 over 3 minus 8, 2 minus 3. And then you solve for lambda. It will show you that, well, you have 2 situations. For the first one, you have lambda is equal to 16 over 3 times 1 over 2, so that will give you 8 over 3. And then that's for the first equation. And for the second equation, you end up with -8 over -3, which is 8 over 3. So the fact that we got the same lambda, the same scalar, and it exists, and it gives us the 1 over 3 and -2, it means that these 3 points are concurrent. Again, you can have a look at how they do it slightly differently here. This other skill, let's say you're given a line and a point, and I need the vector equation, but this time describing it through parallel and perpendicular. So I'm describing how I want it to be. Parallel is just basically how we establish the definition in the very beginning of vector equation of a line. So this is my line. I know this is the point on the line, and I know this is the sorry, not in the correct format, intentionally written in a confusing format. This is the x component, so the x component is written as with a 1 and a lambda here. And a lambda being 1. And the y component is written with a -2 and a coefficient of 1 for the lambda. So make sure that you convert it to the correct format that you need. This is the point that's on the line, and this is the direction vector that your line P is parallel to. So this is what it's parallel to. Now, if I want a vector equation that goes through this point and is again parallel to L, it means I'm taking into consideration the same direction vector. So for part A, it's easy. you have the equation as it goes through the point -4, 1, and I'm just going to use a different scalar. It goes through 1, 1. Okay, so the scalar is here. So it's parallel to my line. If it's parallel to the line, it means you're taking the same direction vector. Now, for part B, it has to be perpendicular to your line. Perpendicular means you are taking the normal to the direction vector. They didn't specify which format they needed to be written in, so we can keep it in vector format. But the idea is, if this is my direction vector of line P, then the perpendicular, which is the normal, is you switching these two numbers, which obviously will stay as 1, but then the second component will be negated. So whatever was your D1 will change signs. So you have 1 and -1 as your direction here, which means now your point is, let's call it W, will have this point that it goes through plus, let's pick gamma, 1 minus 1. This is now the direction vector because it's perpendicular to the actual parallel line. Again, similar questions you've seen in gradient intercept form. You've dealt with this where you need to do the perpendicular, so you take the negative reciprocal and so on. So it's the same idea, we're reciprocating and negating here. They're writing it in the algebraic form, and you can do the same as well. Last question will be just dealing with the same idea, but in 3D. I need to show that a point does not lie on the line. And similar to what we did a few slides ago, we were trying to see if a point goes on the line, and we found a nice lambda that fits with it. Well, in this case, we should get a contradiction, so let's test that out. So what I'm going to do is, again, we will write this in a nice vector form. So our line R is 1, 2, and 0. And lambda is -1, 3, and 2. The way you can do it is you can expand these out and then combine the components, as in the I, J, and K, and then the lambdas on their own. It will be obvious that this is the line. So we want to show that 1, 2, and -3 does not lie on the line. So 1, 2, 0, lambda, -1, 3, and 2. So the idea is we can take these separately. So I can consider this first and say, well, if it does lie on the line, then a 1 minus lambda should give me 1. That's for the first equation. And also, I should get 2 plus lambda, giving me a 2. So 2 plus, 3 lambda should give me a 2. And then a 0 plus 2 lambda, so 2 lambda should give me a -3. Well, if I solve this, for the first one, I'll end up with lambda equals to 0. Second one, I'll end up with lambda equals to 0. But the third one, I'll end up with lambda equals to -3/2, which is a contradiction. So point D does not lie on the line. If they were all 0, then it would have lied on the line. And then part B, find the vector equation parallel to L and pass it through point D. Again, quite easy, similar to the ones before. We have the point D, 1, 2, -3, plus, let's pick mu. And it's parallel, which means it will have the same direction vector, -1, 3, and 2, and mu is a real number. So hopefully these questions gave you a nice insight into how You should deal with vector equation of a line, how to solve them, how to approach them. It's very important to understand how the equation of the line is set up. Where do you substitute? When do you substitute? When do you make things equal? When do you convert them into different forms? What do we mean by parallel, perpendicular, and so on in terms of vector equation of a line? And that will help you answer any type of questions you would face.